Good afternoon, everybody. It's awesome to welcome you to ADC and to our workshop, DSP in Practice. First of all, it's my pleasure to announce that we're fully booked. But the thing is that if you haven't booked a spot and you have sneaked in, it's all right, unless someone who has booked comes in. Then just please leave the seat to them. But other than this, I think we're good to go. So in this workshop, we'll take your idea for an audio plugin through all stages that you would normally have in a professional plugin development, up to a full-fledged plugin that can run in a DAW. So who we are people who once wanted to make plugins, just as maybe some of you want to, or maybe some of you are doing. My name is Jan Wilczek. I'm a founder of the wolfsound.com blog and the YouTube channel. I'm also a host of the Wolf Talk podcast, where I interview people from the audio industry and like developers and researchers. Starting last year, I've been working on JUCE's YouTube channel, on the YouTube channel of the JUCE C++ framework, and I'm also an ADC mentor. And today, to help me in organizing this workshop, I have with me Linus.
I'm Linus Corneliusson, and I used to be a mixing engineer, mainly working in the metal market. Recently, quite recently, like a few years ago, I transitioned into developing. So that's what I'm doing now. For this workshop, I will keep track of the online questions. Please refer them to the Discord channel. I will not see what pops up in the Zoom chat. So Discord is the place for questions. Thanks, and back to you.
Okay. So let's start with a quick survey. Is it your first time at ADC? Okay, let's wait a couple of seconds still. But I think it won't change so much to see that majority of people are beginners at ADC and maybe also in plugin development. And I think it's a wonderful place to be here. I think transitioning to this industry is always much easier when you're talking to people who have already done it. And that's at least the impression for me that I have. So let's take a look at the outline. What we'll do today, first and foremost, we'll get the code to run on your computers, and then we'll immediately proceed to working on a plugin from scratch. We'll start with what I would call digital signal processing research. Then we'll proceed to the Python prototype. Then we'll have our first surprise waiting for us. Then we'll have a break, hopefully at 3 p.m., not later. And after the break, we'll proceed full on with the C++ implementation of our plugin. And after a brief summary, we'll have 2 more surprises waiting for you. So it's a workshop chock full of surprises. I think there's one thing I wanted to mention. Okay, one thing before we progress further is that it's okay to be lost. We're a diverse crowd with various levels of development. And if you have a question, then please interrupt us. Last year, I think I was in the middle of discussing something delay related, and someone in the audience asked me, okay, but what is a delay? And it's a normal question to have. And we are prepared as best as we can to answer such unexpected questions. And the goal of this workshop is to have you learn something. So that's why I think it's best to interrupt and ask questions. Like, do you have any questions right now? No? Okay. This is what you can see on the slide. This is your task. This is the problem that you have. So you have a client that comes to you and says, create a flanger as a VST3 plugin. And in a comic book, they would say you have 24 hours. But the question is, like, what do you do, right? You want to create a plugin, or someone would like you to create a plugin. And what is the procedure to actually go through to create one? And in this case, we'll focus on a flanger. So I just want to briefly present to you what we'll create. I have a Reaper session open. And let's take a listen at the clean, unprocessed signal that we'll listen to a lot today. And ideally, after this workshop, you will have a plugin that looks like this and sounds like this. And the slider is not a fake, it actually works, so we can test it out. Okay. So that is our goal. And now we're on to task 1, or task 0, should I say, to make the code run. So I've sent out a brief email with the instructions to get started. And I know that people who are online, they maybe have access to faster internet. But there are a show of hands, like who has gone through the preparation stage? Okay, that's quite a lot, actually. So that's normally the biggest problem of having such a workshop, is that it turns out that a lot of people need to download all the tools, etc. So we have basically 2 options here. The goal is, what you should be able to do is to run these 2 commands. The above command, the Python command, just verifies that you have everything related to Python installed. And the other command is compiling the C++ project. Everything is discussed in the Getting Started section of the README file. But if you have not cloned the repository and you probably don't have all the necessary tools installed, we have a backup for you. And this is using GitHub Codespaces. So GitHub Codespaces allow you to run a Linux machine in the cloud. And thanks to this, it has all the dependencies installed. So if you have not cloned the repo, not installed the dependencies, what you can do is go on GitHub under this link, github.com/janwilczek/adc25-workshop. And there, you should fork the repo with all the branches. This is important. So we need to uncheck this copy the main branch only. And once you do it, you should be able to create code space. And here on the repository, there's this code button, and you click out code spaces. And then on your repository, so not on mine, but on yours, you create code spaces on main. So we'll now spend a few minutes, waiting until everybody gets up to speed. And if you have already completed this and you have these 2 commands running, then please help your neighbor, okay? Because that's also nature of these workshops and of ADC, to collaborate with others. So we'll be here and we'll be walking around and checking if everyone got up to speed. Okay, can I have your attention for a second? I know there are a lot of hiccups. We try to foresee some of them, but yeah, I'm also surprised that it doesn't work on Python 3.14. It does on 11, 12, and 13. So yeah, there you have it. But if you're running the command somewhere in the background, I know they're taking some time, we can safely proceed to the next part, because I'll be doing a little bit of the talking, and then we'll proceed with some exercises. And I really would like to get to the Python prototype before we get to the break. And I saw that most of the people got Python working, at least. So if you haven't and you cannot get it to work, then please join your neighbor who can run it. So here we would like to take a look at the overview of the plugin creation process, just super briefly, without going into much detail, that's what we're doing today. Actually, can you turn like the volume on this down? Okay, because it's really annoying. Okay, so first we have an idea, right? In this case, the idea is we have a client that comes to us and says, you need to do this. You need to create this plugin. But if you're a sound engineer and you have a clear idea of what you're after, that's the stage you're at. I mean, Linus, can you share a little bit how it's Bogrand, how it is with ideas, where they come from?
Yeah, sure. Normally, it's an idea from the boss who needs something working better in his workflow, or just wants to do something that he thinks will be useful for others. And then we usually try to get quite quickly into a prototype step so that we can start iterating. If it's something we are already used to, then that can be pretty quick. If we need something new, like for example, a specific effect that we don't really have, that's where we spend some time on the research step. And that's pretty much it, like this graph. Try to get a prototype, test it out, go back, what do we need to change, what works, iterate some more. As soon as possible, get to like as final as possible plugin, because that's when you really start to notice that like, oh, this doesn't really work as well as I thought. So then you can quicker end up with a final result.
And am I right in thinking that when you have the implementation in place, then you give the plugin to your boss, and he's like merciless testing it with all the possible parameters, just to get the ones you fix and the one you don't?
Yeah, exactly. I guess we'll touch on that later with the dev parameters and stuff. But absolutely, he tries a lot of things, and then we bounce back and forth until it sounds as he wants it to sound. Okay.
When you have an idea, I think it's good to think about this in this concept of these questions, right? And if you can explain it in plain words what it does, then I think it's goes a long way to start working on the thing. So once you know what you want to create, and we know we want to create a flanger, and that's how it sounds. Then we need to go to the research phase. And here's, we ask ourselves, has someone done it before, right? Because if there's an exact same plugin on the market, we may need to think about our strategy there. I think when we collaborated, it was very useful to find a baseline, right? We found a plugin that was doing something similar that we wanted, and I think you listed everything wrong with this plugin, everything we would like to improve upon. And so we arrived at how to do it, or how to do it better. And then the product of the research phase is a design. And what's a design? I'll elaborate soon. So when you're doing research on the signal processing part of your plugin, these are the sources I would recommend. So first and foremost, we have textbooks, which are, it is grounded knowledge that has been widely accepted to be true. And frankly, it's the easiest one to reach out to. Then we have research papers, which are newer, that has not yet made it into textbooks. Then we have online blogs and videos, forums, and of course, we can pay someone else to do the research. So when it comes to books, these are like two Bibles, I think, of audio effects. We have the digital audio effects, which is a group work, and which is more, let's say, scientific. And then we have designing audio effect plugins in C++, which is more oriented towards developers. When it comes to research papers, consider browsing first the archives of the Digital Audio Effects Conference, the DAFX conference. Like all of their publications are available online. Unfortunately, not so much for the Audio Engineering Society library. There you have to pay to access the articles, but it's still possible. And if you want to look for papers on certain DSP topic, also consider using Google Scholar instead of Google. When it comes to online blogs and videos, I'm sure you can do a better job of listing the ones you like. I'm surprised always to see the wealth of knowledge that's available there, even from researchers, not just from practitioners. My blog can serve as an example. When it comes to online forums, it's amazing how much time professionals are willing to dedicate to share their knowledge. So don't be afraid to ask. For plugin development, but also DSP research, JUCE forum is a very good resource. I'm a member there. There's also KVR Audio Developer Forum. But a lot of amazing DSP engineers, people who work at the largest companies in this industry, hang out at DSP subreddit, at DSP Stack Exchange, which is like a Stack Overflow for DSP. And also when it comes to analog hardware, you have DIY Stompboxes or Lines Forum. And it's incredible how much knowledge there is. Then, when you're after the research phase, we have a design. So this is like a DSP diagram. And this can consist of difference equations. What these are, we'll see in a moment. But this can also be a textual description or a reference, right? We're just going to implement this paper from start to finish. Let me look at my notes here so that I don't skip anything. Okay. Linus, do you want to add anything on the research phase?
No, not really. I think you covered it all. We usually just pay someone who knows better than us, and then.
Okay. And that leads us to a literature review, to the research phase on our flanger, right? And we start looking for a flanger implementation. And as I said, we have books. And in the first book we have a flanger implementation. Now, can people who can read such diagrams raise their hands? Okay, so yeah, somewhat. I mean, some people are not sure, and I understand, because this notation is very informal, right? It's just what does a cross mean? Like here, it's multiplication, but in a different diagram, it may mean something else. So there's always should be always a textual description. And for me, especially this notation here in the rectangle, I mean, I guess it is a delay, right? But what does it actually mean? It's not very clear. And I remember the description doesn't go a long way to explain this. Apart from the diagram, we get this nice table which lists the coefficients, right? We have multiplication here, here, and here. And here are the values of these coefficients. And we also have some modulation. That's how it looks. Okay, but the nice thing is that the textbooks will always have references. And indeed, if we dig deeper, we see that the design from the textbooks comes from a research paper from 1997. And that's actually what was proposed. And frankly, I find this diagram much easier to understand. Just, a quick explanation of what happens here. We have yet another notation here, but okay, we have some input, right, that goes from here. Okay, and then it splits into two paths. One path goes directly to the output, and the other path goes into this delay line. And out of this delay line, there's a feedback back to the input, but there's also an output that changes, right? It's a variable delay line. And this is what's regulated by some oscillator, which we typically call low frequency oscillator. And as we see in the table, it goes from 0 to 10 in the period, right? So in the length of the delay line is modulated from 0 to 10 using a low frequency oscillator. And how it looks, it's we have a signal like this. This is on the left, you can see a regular sign. On the right, you can see something that's a unipolar signal. So it's only from 0 to 1. And using such a unipolar signal, we can change the place from which we take the output from the delay line. Okay. That leads us to our task number 1. So we have this design, right? But we need to somehow conceptualize this to be able to implement it. And we want to implement it in Python first as a prototype because it will go faster. But I wouldn't be able to sit down and just write Python code that implements this. So we want to derive something that's called a difference equation. So relation between the output y and the input x. And now I would like to that instead of leaving you, with this task of writing the difference equation here, I'd like us to attempt to do this together on some simpler examples. Maybe, are there any questions at this stage before I jump into this practice? Okay, that's not good. Okay. So how we can think about this? We have some system, and it has an input x of n, a signal consisting of samples, and at the output of the system, we denote such a signal y of n. And here I created like a 3-sample input signal, and we want to predict how this will look at the output. So our task is once again to write out the difference equation for this system. So here, let's do, yeah.
I might have missed this, but how does the difference equation relate to the block diagram specifically? Is that the bit in the middle?
Yeah, exactly. So it's a diagram and the difference equation are 2 different representations of the same thing. So exactly, the difference equation relates the output to the input. And a block diagram does the same.
So what's the difference between the input and the output? That's what the difference.
I think the name different comes more from mathematics, in the same that we can portray one thing in terms of the other thing. So we want to portray the output just as some function of x. So we write y equals x something. I think that's the general idea. Does it answer your question, or is it just more hand waving? Okay. And generally, difference equations are easier to implement, or in other words, that's what we implement. So in this first instance, we have a system that does nothing, right? So the output is equal exactly to the input. And if I were to draw, I would draw exactly the same input here as the output, because nothing changes. I mean, such a system is useless, basically, but it illustrates how we map between the input and output. Let's look at example number 2. Here, we have something like this, and this is my spin on the multiplication. In the diagrams, we had a cross, I think. This is multiplication by Jan, so we have y of n equals 3x of n. So this is basically a gain, right? We increase the signal's amplitude by 3. So this peaks here will get 3 times larger than in the input. Okay, now we are in system 3. And here we have z to the -1. This is what's called a delay. So we write y of n is equal to x of n minus 1. And what this means that, sorry, maybe let me move here, that the output is delayed by one sample with respect to the input. So the first sample will be 0. This is our delay. And then as the second sample comes the first sample of the input. And as the third sample comes the second sample of the input. And if we were processing further, the third sample of the input would also appear. So this is where it gets already trickier, because we have this notation here in the brackets. And it starts to get confusing if you're not used to this. So now let's be a little bit more confusing. And instead of having a delay by one sample, let's have a delay by n samples. So what should I write here? Y of n equals what? Is there anyone who wants to risk an answer? Yeah.
N minus big N.
X?
N minus big
X n minus big N. That's correct. And it means that big N, capital N, this is a parameter, right? So in code, we would set n to something, and then we could determine the length of this delay. So this is yet another level of abstraction. Like just above, we had a delay by a single sample. Now we have a delay by a variable number of samples. Like this is parameterized, okay? And this will come in handy because we have a modulated delay line, right? So the delay length will change. Let's do one more round. We have y of n, assign, and what we have here, we have a plus sign. We have two input signals. Now, what will be the equation for the output, the difference equation? We take two signals, we sum them together, and we get an output.
X1n plus X2n.
Perfect. X1n plus X2n. Okay? And now we can mix and match all these to get basically an arbitrary DSP system. Like whenever there's something more complicated, it's typically described in text already. But this can get you pretty far. So with this out of the way, let's take a look back at our flanger diagram. Okay. How do we approach even, like doing something like this? I think I try to draw, and I see if I can draw here. Perfect. So we start from the end, because we want to write y of n equals something. So we start from the end, and we trace back what goes into the output. Here we have summation, right? So we will have something plus something. And we go one route, okay, and we meet multiplication, right? So one of the summands will be the blend coefficient times, this is multiplication. And then we go back and we see xh of n. Okay? So we have one branch of this. And then we trace the other branch, and we see another multiplication, and we have feed forward. This is a multiplication coefficient, and we go back, and we see xh of n minus m. Okay, now what is xh of n? Like, we don't want just xh, right? We want to x of n. And now this is another trick here that I introduced, because we have, let me switch. Yeah, spoiler alert. We have a feedback here. And this feedback makes the analysis even more complicated. I mean, it's super compact to have such a DSP diagram. And maybe you show it to a software engineer and they're like, okay, I get it. But to me, it's really requires careful analysis because feedback is not intuitive at all. So what we do here is we add this marking, right? We say at this point, we denote this signal by xh. And now we see that the signal enters the delay, and we can see that the output of this delay can be denoted in terms of the helper variable. So yeah, we have the equation for the output, but in terms of helper signal, not of the input signal. And so now we need to derive what is xh of n. I don't know if I'll manage to do this, but I'll try. Okay, xh of n, what it is? Well, what is like the obvious thing that goes into xh of n? xn, of course. We'll have xn plus something. Now, so we go this other branch, and what do we have here? Multiplication, right? So we have feedback times something. So we go back here, and here a friendly hand wrote us what exactly should be here. So we have xh of n minus d divided by 2. What is d? I'll explain in a bit, but you may wonder now we have xh of n defined in terms of xh, which is suspicious, but this is exactly what feedback is. And we can do this because we have a delay here. So xh of n is the current thing, and this xh of n minus d2, d divided by 2, it's a thing of the past. So we got it already. It's a known thing. So that's why it's correct. And so we're almost there because we have defined y of n. We have defined xh of n. But the problem is that we have also these delayed guys here. We have xh of n minus m. Maybe let me switch to this one. We have this term and this term. And again, this is a fixed step based on the design, right? I'm not making this up. I've taken it from an article. So there's a fixed delay. Fixed delay is relatively easy to implement. This is what's more problematic because we have here some m, and this m is a modulated tap. It's not a parameter that we set before we create our plugin. It's something that changes based on our LFO signal. So this m will change with every update. So the last equation that we need to have here is the one for m. And frankly, I'll just show it to you. It's just the value of the LFO, which is from 0 to 1, multiplied by the length of the delay line. And here are our three update equations. We have the one for the output, which is defined in terms of xh. And we have xh in terms of xn and the past xh. And we also have how much we have to delay xh in the feed-forward branch by calculating this m. And note that we moved backward from what we want to achieve. So the order we apply these equations is reverse to the one we obtained them in. So first we calculate the delay, then we calculate the helper variable, and then we calculate the output sample. Are there any questions to this part? If that's confusing, that's okay, because we'll be implementing this in a bit. And to me, at least, when it's always easy to understand when I implement it, and then when I hear it, it starts to make sense. So the question is, why do we have this feedback here with a static delay? Something that's not changing while the effect is running. Yeah, this is created to change the timbre of the delay input even more. So if, I'm not sure if I can depict this. This would be even more hand waving, but let me try. I do it like this. I'll try to copy this here. Okay. Yeah, let me hide this part. And this part. It's okay to look at just this part and consider what it does. And this is like, does anyone know what this actually is? It's a feedback com filter, right? And so this is something that you'll see when you run the Python when you run the Python test. You generated some spectrograms, and you were able to see the troughs in the spectrum that are caused by a feedback com filter. Maybe I'll type this in. Feedback com filter, which is a super useful thing. And so the goal of this is to further enhance spectral or sonic properties of the signal before we start to messing with the delay. But then, if we look at the other end, we have a feed-forward com filter because we have a direct path plus a delayed path. So we also get feed-forward com filter. I mean, there are entire papers written on the analysis of such systems, but that's the essence of flanger, like combination of these two plus an LFO. Does it answer a question? Kind of? Yeah, let's chat after or in the break. Okay. Any other questions, or is it okay that we move forward?
Okay.
Yeah, there's a question on Discord.
Yes. Maybe you covered it.
Sorry, so xh n minus m doesn't equal xh n minus d divided by 2. Yes, it does not equal. That's true, yeah. So let's think about this. If the LFO is exactly half, right? If the LFO is exactly half, so this is half, then m is equal d divided by 2. So then they are the same sample that we output here. That we output here and here. Is there any reaction?
We will find out.
Okay, maybe I can get back to this.
There is one more question we
Oh,
can
yeah.
cover. So another question is like, how can it come out of the box twice? But that's simply, we're just reading twice from the delay line. I think it will become clear when we look at the code, right?
Exactly. Like, let's think, like, if we are programmers, it's easy to think of the delay as just an array, right? And if you have an array, we can just read out of the array whatever we want, how many times we want. It's just when we update the array, then we move the samples and something changes. When we look at the code, this should become clearer, I think. Okay, we arrived at our prototype. Let me look at my notes so that I'm sure that I won't skip anything. Okay, so prototyping, we want to quickly create as fast as we can. We want to hear our designs. And sometimes it's not easy, right? If we have an effect that embeds a neural network that we have to train, like even getting to the prototype stage is already quite a lot. But traditionally, I listed on the slide the tools that are used for this purpose. And I'm just curious, like, can I just ask who has used these tools? So for example, who has used Pure Data? Okay. Who has used Max MSP? Okay. Which one's better? No, I'm just joking. Then who has used Python? Who has used MATLAB? Oh, a lot of rich people. Okay. And then there are domain-specific languages, which have a lot of fans in the internet. And I confess I didn't have time to just learn these. I'm just going with Python all the time. But who has used Faust? Okay, I see 2.5 people. And then Super Collider. Okay, some more. Okay. So Linus, do you want to comment on how you prototype at Bogren?
We try to stay in C++ as soon as we can, but that's maybe a bit specific to us since we need to start working with Jens. He needs to get his hands on all the minor parameters to tweak stuff behind the scenes. So we try to stay in C++, but for some things, for example, when we collaborated with Jan on an Octaver, then you started in Python, which was very, very, very helpful, I would say. So if you have this clear idea of what you're trying to do and there is a good reference for it, then I would absolutely recommend, like we're doing now, start in Python, make it work, and then have that as a reference to fall back to. Yeah, pretty much like that.
Okay, thanks. Okay, now we arrived at our second task. And this is something that will take us time until the break for sure. Please check out the task branch. Like, this is important. And then run this test, or you run the one with the guitar. And on this branch, the output that's in the output folder should sound the same as the input because we haven't implemented our prototype, right? So this script, this main.py, let's see what it does. Is it visible on the screen? Is okay? Okay. I hope it's visible on Discord as well. So what you'll be working now here is a py directory, and you work in the flanger file. Just let me show you what the main file does. It basically reads the file we pass to it and then applies flanger onto it. And the flanger, this apply flanger instantiates the flanger effect and processes it, like sample by sample. Okay, and let me check out task 2a. Okay, perfect. And we have this very basic flanger class that doesn't do anything in its process sample. It returns the input sample. So instead of giving you instructions orally, here in the README file, maybe let me even create open preview. Oh yeah. So here you have the description of the flanger, and here you have the update equations as well in the README file. And then here you have precise instructions what to do is in task number 2. And what we're aiming for is we first want to create a flanger effect without the LFO, without changing the delay, and then we'll add an LFO later. So here, like, I don't want to go over this because like you can read, but we'll be here to answer, you know, all of your confusion. And from last year, I found that these instructions were pretty straightforward. So once again, on the high level, run this command, inspect the spectrograms, listen to the output, and then start working on the flanger class so that audibly we get to the sweet sound of the flanger with the changing LFO. And since we are 4 minutes to the break, I think it's a good time to do this. But before, I mean, oh yeah, as the first surprise of the day. So this is the part where we unfortunately torture the people online. But tomorrow is Poland's Independence Day. And on this occasion, I brought you from overseas one of Poland's finest. And this is called cream fudge, I believe, in English. And it's certainly gluten full and lactose full. So if you cannot, and calorie full, of course. So if you refuse, I won't be mad. But yeah. So yeah, I realized that we took a bit of time with the setup. So what I suggest is checking out the next task branch. Check out task 3A. And now let's take a look at the solution. So, and let me open maybe the README file side by side. If someone in the Zoom has trouble seeing the code, then let me know. Okay, we are at task 2. We have the update equations. We run the Python function, and we inspected the spectrograms. Now, what we do? Well, we set the max delay, and we calculate it from milliseconds to samples, right? So that's our D. That's what we had as D in the diagrams. Then we instantiate the delay line and pass it the max delay. And then we calculate the index of the tap, right? This is our D divided by 2. This is our fixed tap. And then we just set the values of the coefficients, which I have seen that you've correctly set. And then what we did in the second part is that we instantiate the LFO with a given sample rate, and we set its frequency to 2 Hertz. Okay? So that's the setup that we have. There was a question, and I think it's a very good question, of how we remember past samples between calls to process sample. That's what we have this fractional delay line for. So once again, what do we do when we process sample? Maybe let me display this diagram here. We first start, or maybe let me display the update equation. So first, we calculate the M, so the currently modulated tap. So we get the value from the LFO, and then we make it unipolar, right? So the LFO value is from -1 to 1, +1 is from 0 to 2, divided by 2 is from 0 to 1. And that's what we want, a unipolar LFO, just as we've seen here. So we went from the left signal to the right signal. Then we calculate the delay, the M, right? That's the one that changes, and it's based on the LFO value. And it's simply the delay, the maximum delay, times the LFO unipolar value, just as we have in the first equation. And then I used also the same notation as in the equations, so it's easier to compare. And it's the same I did here. For x, I took the input sample. And then we proceed with the second update equation. We calculate the helper signal. Xh is x plus feedback, as we have here, of delay line, and we pop the sample from the middle. This is the fixed tap. So we already have Xh. And then we calculate the output, and that's again this equation. So simply it's blend times Xh plus feed forward times pop sample of M, so M, the variable tap. And what we do, it's the last step, it's we push Xh into the delay line, just as we had here, just as it enters the delay. And that illustrates an important principle that whenever we're dealing with delays, with delay lines, something Z to something, we first calculate the output, and then we update the buffers. That's the main rule. First calculate the output, and then update the buffers. Because otherwise we get into this frenzy of, we need to update the delay, but we need to calculate the output, but we need to update the delay. So that's a good rule that to follow. And that's it. That's our whole prototype. And first of all, it's very fast to set up when you download all the dependencies, right? And the second of all, we can look at the code and have a good comparison with the equations. So that's what engineers often do. They exactly have the paper open, and they'll type these equations, and they'll use exactly this notation, right? Xh, etc., which can be super confusing if you don't have the paper or the diagram, but we have the diagram here. So it should be then clearer. Okay, so we have the Python prototype. Are there any questions maybe at this point? Okay. Then we proceed to the implementation. So we actually start to implement our plugin. And this is typically done in C++ with JUCE. I know that there are other solutions out there, but in professional plugin development, I haven't seen anything other than C++ with JUCE, to be honest. And I think that's the same, even more true for Bogra and Digital, right? Where even the prototypes you have in C++.
Yeah, exactly. And with JUCE as the backend, of course.
Okay. So how I like to approach this, because we have a prototype in Python that somehow works, but we want to have C++ code that works the same, right? So it's always risky because when we implement C++ code, we can make mistakes, and we want to have exactly the same output as in Python. So a good rule of thumb is to start with mono first. So just process a single sample, and don't focus on parameter smoothing, but focus on correctness, disregarding optimization. So we don't want to make our code run fast in C++. We just want to make it run correctly. And this where the GUI just used this generic audio processor editor and use these end-to-end verification tests so that you can compare your C++ output to the Python output. And then you can also do these null tests, right, when you subtract the two signals, C++ signal, Python signal, and you verify that the output is 0. So here I put some implementation tips for you. I don't want to go over them so much, but what I would like to underscore here is writing pseudocode, writing unit tests, which we'll do, treating warnings as errors, And you also see that it's useful to keep this structure in mind. So, you know, in Python, this was offline processing. We just had initialization and then processing. Here, we have initialization, all right. We have prepare, and then processing, we have process. But we also need to remember about resetting. So what should happen when the playback stops? Okay, do you want to comment on the implementation part?
Yeah, just a quick note on that to try to leave details for like later, keep it simple. So it's hard to see on this one, but here's our processor graph with a bunch of DSP blocks. We have parameters we can tweak for them under the hood that the user can't see. We can connect to them with a JUCE generic editor. It's hidden by the Finder window, but here is like a completely generic editor that we didn't have to put any work into at all. So just make it work. Don't focus on making a nice UI or anything. I guess that's the main takeaway there.
Okay. So that's how our C++ looks, or should look. Again, we have a flanger class, just as we did in Python. We have a fractional delay line class that you don't have to write, just as we had in Python. And then in the end, we'll have parameters as members of flanger and oscillator. But for now, in task 3, we'll focus just on getting the flanger equation out. We don't want to focus on the LFO. So this is your task. Check out the branch, build the C++ project. So maybe let me run this. We're on branch task 3a, and now let me run CMake -- preset default. I'm using a different directory because reasons. And then CMake -- build -- preset default. But yeah, you could type this, or I will simply do local build. Okay, it built. On my machine, it also installs the plugin. And this plugin does nothing, right? Because it's task 3. There is no implementation, but it's a skeleton that just outputs the input. Okay. Now you can test it in we can run the end-to-end test. So let me run this. This is local build. For you, I think it's going to be the build directory. And then there's test and audio plugin test. That's one way to run it. Okay. Obviously, stereo test failed because it's just mono. But we have the end-to-end test here. And if we open the sidebar, again, in the output directory, we can see we have the saw output, flanger test file end-to-end output. And this is the Python one. So we have C++ and Python output, and we'll be able to compare if we're getting closer. Okay, so we run the end-to-end test. Great. Now we want to test in a DAW. Yeah, let me close the Reaper and reopen it again so that it scans again the plugin, as you can see here. Okay, this is my plugin, and if I play it out, it just returns the input. It doesn't do any processing because that's our task here. And now we need to implement flanger member functions, and in the end, make the end-to-end test produce the same results as fixed delay Python code. Okay, and for this, again, the instructions are in the README file. Here we go. Okay. Perfect. So we need to add feed-forward feedback and blend coefficients as class member of flanger. Let's do this together. So we have our plugin directory. And here, that's what we said. We want to get to the working plugin as soon as possible. So we just put everything in a header file. It also makes it easier then to use different sample types. Here, you don't have to worry about this process stuff. This is something when we're using process context from JUCE. It's not important. We have this function, process sample, reset, and prepare. And that's all we care about. OK, so our task here is to add feed-forward feedback and blend coefficients as class member of class flanger. So that's simple. In the private section, we write float feed forward, assign 0.7, and then float feedback, assign 0.7, float blend, assign 0.7. Is it correct? OK, everyone hopes it's correct. We can see here. Yeah, these were all 0.7. Again, that's where Python prototypes come in handy. All right, then we need to add a fractional delay line. This should be also easy. Fractional delay line, delay line. And now we need to implement flanger reset, where we reset the members. This is quite easy. Like, these coefficients are constant. So we need to just reset the delay line. Reset. OK. And then we need to add max delay and middle delay members to the flanger class. So just as we did in the Python class. OK? So once again, we go float max delay, and we assign it 0, and float middle delay, and we assign it 0. I can make these floats, right? Because this is a fractional delay line. So I can read out samples not from direct indices of the underlying buffer, but I can leverage the interpolation that the fractional delay line class does. OK. As you can see, we're just porting what's in Python. Now we need to initialize them in prepare with the same lengths in samples as in Python. OK. Here we receive a process spec. Let's take a look what it is. It's sample rate, maximum block size, num channels. What we actually need here is probably we need to initialize the delay line first. Let's see if that's the case. No, that's not even, it doesn't even need the sample rate. OK. So the only thing that we need is max delay and the middle delay. OK. So if I remember correctly, we had auto max delay milliseconds. It was 2, right? Yes. And now we need to convert it to max delay in samples. So max delay is sample rate spec sample rate times max delay ms divided by 1000. So max delay in milliseconds divided by 1000 is max delay in seconds, and then multiplied by sample rate is max delay in samples. Okay, and then what we have in here is the middle delay. It's simply max delay divided by 2. Middle delay assign max delay divided by 2. Okay. And now we have this one. But before we proceed, I'd like to check if I'm doing the right thing in the prepare. So let me go git diff task 4a. Okay. Okay. See, I had a little bit different approach. Okay. And then these, okay, I simply cast a sample type. Yeah, but this is very similar, maybe with the exception of the ceiling function. That's what I forgot to import from Python. Okay, and this will implement shortly, and the coefficients are here. Okay, this is here, perfect. So now we need to implement update equations in process sample. Here we are, process sample. Okay. So let me just open, Python here on the side. And we disregard this stuff for now. So we disregard LFO. So once again, we can do something like this. Const auto x sample. So that we know that we have x. Okay, and then we can write const auto xh, x plus feedback times delay line, pop sample with delay, middle delay. Okay, middle delay. Okay, that's one part. And then the output const auto y blend times xh plus feed forward times delay line, pop sample. And here we need to make up number. So I'd like to use some fixed one. Let me just check what I used in the solution here. Okay, I just used the last one simply. Okay, so I haven't passed any argument. Okay, and then we should, of course, return y, but we cannot forget about updating the buffers. So we go delay line, push sample, and here we have xh that goes into. Okay, now we need to build a project, CMake -- build. For me, it's local build. Okay, something doesn't work with implicit conversion. So let's go here. Okay, static cast, float, sample rate. Let's try again. Okay, it worked. Let me run the end-to-end test. So this is going to be, once again, local build test audio plugin test. Okay, this end-to-end test runs successfully. Okay. And now let me look in the output folder. Here it is. Oh, wow. Okay, let me change the test file then. Source, measure end-to-end. Okay. Tar 5th.wave. Okay. Bless you. Okay. Let me play it out. Is it different from the original? Let's see. And now the flanger one. Can you hear a difference or not? Not much. Okay. Okay. I think that's the issue with having no LFO, and that's why we'll have task 4. But before this, it's important to mention that once we have our project in some state, we may want to tweak stuff. And that's what Linus kind of already alluded to, that they expose loads of parameters and they play with them. And then, the end user only sees a handful of them. So that's why it's also interesting here to explore, change the ranges of the parameters, make them extreme, make them crazy. That's sometimes called model bending. But it really pays off to explore at this stage. And we want to enable this. But first of all, we need to deal with this LFO. So let's try to implement one using the oscillator class from JUCE. Let me check out task 4. Maybe save this one. Okay. Okay. Thanks to JUCE, this is quite straightforward. We have a appropriate class already available in the JUCE DSP namespace, JUCE DSP oscillator of sample type, and we'll call this LFO. And now in the prepare member function, we need to prepare this LFO prepare spec. And in the reset function, we also need to reset it. LFO reset. Okay. And then we want to set it frequency. Maybe let's set it to 2 Hertz. Set frequency 2 to match the Python one. And now we need to take it into account here in the process sample. So again, let's go cons auto unipolar LFO. And this is LFO process sample to get just a single sample of the output. And then do you remember what we need to do, right? We need to add 1 to change its range, and then we need to divide it by 2. Okay. Now we need to calculate the modulated delay value, just as we did in Python. So let me check this again. We have cons auto m assign max delay times unipolar LFO. Okay. And this is what we put here. So this is our current delay. And then let me check if that's everything. Okay. And now this should be more interesting.
You should have a field definition.
Which definition should I show?
Section field breadth.
Okay. Okay. We have some bad exception here. Yeah, that's because we haven't instantiated this oscillator, right? JUCE's oscillator always takes phase as the input. So we should return syn here because we want to assign LFO. Okay. Yeah, I want to change it up to guitar. Okay, yeah, let's see. So, you know, with some little difference, we can compare it to Python. For example, we need to make sure that the phase of the LFO is the same, right? But that's how we can approach moving from from Python to C++. So with this basic code, I encourage you to enable the tweaking step. So in the README file, you have instructions, you know, how to make the LFO frequency adjustable. And I think that's also on the slide. So how we did this, I remember we just created a parameter struct, which is an internal struct to flanger with all the parameters. And for now, it would have just a single LFO frequency parameter. And then we need to expose it as a parameter of the plugin. So we create this audio parameter value tree state. And we initialize it, we initialize it in the plugin with our new parameter. So that's what I think we'll focus on now. And then we'll give this, I think, like 20, 25 minutes, and then we'll conclude. Well, we'll do a brief interruption, and then we can continue. So I'm not sure how long should we go, because it says 180 minutes, but in the schedule you saw that it's until 5 p.m. So what we'll do is that we'll wrap up now, and if someone wants to stay, we'll be happy to help him out until 5 p.m. No problem. But we also feel that there's some cool stuff that we want to share, and so let's not postpone this. You know, this is something that you know, Linus already kind of alluded to. That when we have a ready plugin, we can give it to someone, right? And then in case of Bogran, it's Jens who's tested this extensively. And then, you know, how does he go back to you with feedback of the ready-made plugin?
Well, he screams loudly in the studio, and then I come running. That's pretty much it. So if he has tried something with a prototype, he always keeps that session ready. And then he gets the final plugin, and then he basically A/B listens, and usually phase cancels them out against each other, if you're aware of how that can work. If you flip the polarity of one signal and add it to the other, they should theoretically become silent if they are the same. So then he can do that and make sure that they are actually as expected. And if they are not, when they are not, then we will just take it from there and see why it didn't work and what could go wrong. Yeah, so then we just go back and forth, back and forth.
Exactly. And then when you have the plugin and you can listen to it, you can test it out, then you can iterate, you know, on your design. And I think at this stage, when you're working with a client, it's very important to establish some criteria. You know, can they specify what they want? You know, what are the boundaries? Like, this is difficult because I think when we work on the Octaver plugin, it was difficult to specify what we're exactly after. But I think one of the things we focused on was kind of quick reaction, so a low latency of the Octaver itself. And then we were able to pinpoint problems with the current version and iterate from there. but it's always difficult to set specific metrics. So that's what we try to aid here with the questions on the slide. Please go ahead.
Yeah, I was going to ask, would you ever specify unit tests for a plugin like this? Is that even something you can do?
Yeah, so you can unit test for all the properties that you know, and you can, and I focus on two types of unit tests. So if you look in the plugin project, one, these are tests that you put something out and you can calculate by hand what goes out. This is like a fractional delay line, right? And the second type of test is something that you would also do. That's what they taught me in the studio. You do these end-to-end tests when you invoke all of your system and then you generate a file. That's what we also do here. And then you can keep this file as a reference, right? If something goes wrong, then you know that you see that the output is different from what was there before. You can see that there was a regression. So a bug was introduced. And with these criteria, we can use, I don't want to get into signal processing details here, but there are certain metrics, signal metrics. For example, we can measure total harmonic distortion, and that tells us if there's something wrong with our plugin. And that's exactly what we did when we worked on the Octaver plugin. So we had this back and forth with Jens, and we tried to come up with examples that sound good. I think what was especially important in the Octaver plugin was that there were problematic behaviors, and we were able to pinpoint exactly which signals cause this problem. And the awesome sample that you're hearing right now of the guitar that's playing is actually amazing that was the signal that tripped up, I think, our initial implementation of the Octaver. And the reason is it's because it's a fifth, right? So if you're playing a solo and you have just single notes, it's something entirely different for the plugin if you're just playing a fifth. So, and that really amazed us, that you can play an entire solo and it sounds great, but then you play a fifth and it breaks down. So I think we could play a demo of how it sounded in the end. Yeah, and it's minus 10 dB, so it should be fine. Just for clarity, like that's not just adding an octave, but that's like obviously an entire plugin that runs on top of it. But if you can listen, yeah, which octaves are there? Yeah, we can turn them off.
I think you need to activate the Octaver
Which
with
one?
the power button.
Here, yeah. Okay. So let's listen to the direct one. Okay, and then let's listen to octave 1.
And just to mention, the tricky part here is that this is what we expect. We want the lowest note to be octave down, but it was really hard to make it realize which is the intended lowest note in the fifth thing. So that's why we had to make this test with this specific signal until it didn't fail. That was easier said than done, just as an example of how to test and iterate, I guess.
Yeah, and then when you add these lower octaves, you're able to get these richer, fuller sounds. Yeah. So that's what you can produce, with this approach. That's exactly what we did step by step. These are the steps that we didn't cover, but as you can see, something like presets comes way later when we already fix what we want our plugin to behave. And not to mention code optimization, which, is a whole different thing. Here I listed some of the resources that you may consider. Obviously, this is a pitch for my stuff. But if if you were intrigued by the signal processing part of this workshop, then I encourage you to check out my DSP Pro online course. It's aimed at people who are complete beginners. And especially just for this workshop, I introduced a promo code that gives you a discount until December 10. And also, if you have any questions or feedback regarding this workshop or the course, I'll be also happy to answer. Please, you have a question.
Yeah, so I wanted to ask about the GUI. So how do you render these graphics with SVGs? Is it all SVGs or is like PNG sprites and?
For this one,
Yeah.
that's not really my department, but a lot of it is like pre-generated images and image strips.
Yeah, in SVGs probably, or
not necessarily. No, most of it is not. There is a talk. You just missed a talk on this exact thing in the other room. Yeah, it's 30 minutes ago.
Okay.
Sorry about that. Go look at Benz's talk later. I can point you to it. It's going through exactly what we do and how to make it work.
Okay, cool. Thanks.
And exactly on this topic, on how to create GUIs, we have a talk tomorrow with Tom Poole from JUCE, because we're launching the official JUCE course. That's exactly going, let's say, task 4 to building a plugin with JUCE from ground up, explaining, the audio plugin ecosystem, why do we need JUCE, and how to create a plugin step by step. And we have a huge module on user interface design. So maybe some of the questions will be answered there. Yeah. So if you want to go, then we won't be offended, but we're also very happy to help you out. We'll stay here anyway until 5 p.m. And if you want to chat, that'll be great too. So thank you all. Thank you, Linus. And have a great rest of the conference. Thank you for persevering.